Alright, it is about 7:30 p.m. and I just finished drinking a cup of coffee because this video has been a little bit difficult to make, really difficult to try to wrap up in a short amount of time. So if you find anything useful in this, please like, comment, share, subscribe. This video took a while, but in this video, we're going to be talking about integrals. And integrals are kind of this mysterious thing, a little bit different than derivatives. But the way that I think we can start this off to be useful is we're going to consider the graph of a function that's going to be representing sales. And this can just be of some company, where on the right here we're looking at days, and on the left we're looking at the function as it is dependent on days, and that would be measured in dollars because we're looking at sales. And we're going to say that someone just gave us a curve fit function of what's going on. And then somebody else prompted us with asking how much money did the company earn over a year. So what we could do is we could look at every little individual day and find the corresponding data for that and then add those all together. We could divide this up into quarters, and maybe we could try to linearize these points and then just take some average and add up all those averages. And of course there would be a little bit of variation or tolerance here because you can see just by linearizing we are missing some data. And if we consider this interval right here, so we're just going to consider this stretch of 5 days. And we can see here that we have a pretty constant value. For the sake of this problem, we're just going to say that is constant. So we would say for those 5 days, that would correspond to, let's call it, I don't know, $70 million. So for those 5 days, we would have 5 days times $70 million. And if we look at what happened in this little strip here, well, we kind of just took the area of that little strip, right? Because we had 5 days, we had $70 million, and that's our multiplication that we did. And that's kind of the basic principle here, is we would divide this function up into little strips, and then try to make those little strips into rectangles, and then take the value that we would get, and then we would sum up all of those little strips to have the complete area under the curve, and that's what integration would get us. So if we wanted to express this in some mathematical notation, we could say that the total sales, that was equal to the summation, and we can just say that I is equal to 1 to some value n of the value that we got for that function for some interval, and then that was multiplied by that interval, so we could just call that delta x. But the bigger that your delta x is, the more resolution that you're going to lose. But this is kind of the basis that we're starting with. So if we look into making these strips, we can simply define a few things. So in all of these graphs, we're just going to have some endpoints. So we can call this A and this B. And these are just generic endpoints. You can really call it wherever you want it. But we would say that we have some delta x that's equal to B minus A, which again are the end and start points. And that's going to be divided by n, which is the number of intervals that you define. We could also denote where we are looking at in terms of x by x subscript I, which is equal to a plus I times delta x. And it's good to emphasize here that this I does not signify a complex value. It's just the incremental value that we plugged in. You could call this Q to completely avoid this complex confusion. But there's a few methods of how we draw these strips, such that we try to avoid undershooting and overshooting, and it's not a one-size-fits-all. So if we look at these, you can have a left endpoints method. So on some interval, if we look at delta x, we would use that left endpoint. We would go all the way up with it, connect it to where we connect on the graph. So that's right here. And then we would just draw a horizontal line all the way over to the end of that interval. And then this would be our strip. And we would do that for each interval. We could have the right endpoint method. So now we look at some interval, again, delta x. We look at the right endpoint, connect that to where that function is. Now we draw a horizontal line to the left until we get to the, I guess you can say, beginning of that interval, and then carry it down. So now this is the area that we're looking at. And notice here with this part of the function, the right endpoint method actually overshoots it. The left endpoint would undershoot for the total sum because we would not be accounting for any of this area. But as we get over this hump, you can see that using the left endpoint method, now we overshoot here. But there's another method we can use, and it kind of takes care of both of those. You still get a little bit of variance, and it's the midpoint method. So you take the midpoint of each interval until you hit that function, and then you extend in each direction of that interval, carry it down. And now this is the area that you're looking at. Notice here you overshoot, but then right next to it, you kind of undershoot just a little bit. So hopefully the differences are even smaller than using the left or the right input methods. So in other words, if we need to do the summation, we have options. So if we take our equation above, and this is where the magic is going to happen, because what we're going to do is we're going to take the limit as n goes to infinity of that summation. So notice now as n goes to infinity right here, if this gets really, really large, delta x becomes really, really small. So our sampling that we did right here gets pushed towards this infinitesimal sampling, and that transports us to actually having our integration. So our integration is represented by this integral here. We could have some limits of integration. So in our interval, because we're going from a to b, we denote it like this. Now, instead of having this right here, we just represent f as that function, which would be represented here. And then this delta x turns into an infinitesimal dx. And now we've arrived at our proper notation for an integral. And what an integral is? Well, again, it is that total area under the curve. So if we look at an example, and we are interested over the interval 0 to pi, where inside of this integral, we have what is called the integrand. And because this is equal to the area under the curve, this is going to be equal to a number. So that's the notation we need to get comfortable with. And we can have some properties for integrals. First one that we're going to look at, if we have the integral of some constant value c from a to b with respect to x here, well, we know that that's going to be a constant function. So if we draw that graph, so we have x and then y here, we can have some value c, and we can have some interval a to b. We know that that function is going to be equal to this horizontal line. If we're interested about the area under the curve, we know that that is just going to be equal to c times the value of b minus a, because that is our area of a rectangle. Pretty straightforward. So this is what we're given. And we'll actually see how this is useful later on. But the next thing that we're going to look at is if we have an integral with limits a to a of some function with respect to x, that's going to be equal to 0. And looking back above, this kind of makes sense, because if that interval that we're interested in is a to a, so it makes sense that the answer would be 0. If we have our integral that looks like this, and what happens if we flip those limits a and b? So now we go b and a. And what happens is we actually get a negative sign that carries through. And this might be the most confusing one for right now, but we'll see again later on why this is the case. But if we consider the first useful property right here, we know that the result of this integral, or the area under the curve, has to be equal to this. So if we kind of switch places with the a and the b and do that down here, we need to put in this negative sign, because by switching places and plugging in that negative sign, we would get negative c multiplied by a minus b. So we can distribute that negative sign inside of the parentheses, and we would get back what we got back before, which was the area of the rectangle. Notice that shouldn't change. And then if we keep moving on, we can look at the integral of two functions added or subtracted. We can break that up into separate integrals. And then lastly, if we look at the integral from a to c of our original function f of x, we can break that integral up to separate the intervals that we're interested in. So here we had a to c, but we broke that up into a to b plus b to c. Notice we kept the function the same, and this would give us the same area under the curve. But looking into some more things, what happens if the function goes negative, or is less than 0 for some interval? So here you can see this function goes negative for a bit, and this is why I think the sales example is pretty good, because now if you say this was the graph for sales, you would see that you got some money here, but you lost some money here. So if you think about what that means in terms of the integrals now, if you had some value that was negative, you would subtract that from the positive area under these curves right here. And if we consider having two functions, so f of x and g of x, and if we say that f of x is greater or equal to g of x for some interval a to b, well, if that's the case, we know that the area under the curve, or the integral of f of x that's going to be greater or equal to the integral of g of x. And when we have these limits of integration, we call that a definite integral. Now we can also have something called indefinite integrals, which are a little bit more abstract. Definite is for sure the easier route to go, because we know if we have some definite integral and we compute what that is, we get a number. But if we try to compute what the indefinite integral is, we don't really know what we get. But thanks to a few smart people back in the day, where if we consider the definite integral, so the thing that we've been looking at this entire time, it was discovered that you could actually solve this, that it was actually equal to some other thing, call it capital F, at the top limit of integration, so b, minus, again, that capital F, evaluated at the lower limit, or a, and you might actually see this notation here now has a placeholder of x, so maybe we have some function that's going on here, but it's evaluated at b and a. And the new concept is that that capital F is what we call the antiderivative of that lowercase f. Or in other words, the derivative of capital F is equal to lowercase f. And if we look at an example, we're going to consider the function y being equal to 3x. Now we know that the derivative of y is going to be equal to 3. So we can say that 3 is the derivative of 3x, or we can say that 3x is the antiderivative of 3. And this is a very bad way to do this notation, this anti-ddx. Never do that, but just for the purpose of this video, shorthanded it like that. But nevertheless, this is the premise of what we're looking at for antiderivatives. So let's say we want to integrate over the function y being equal to 3 now. So forget about these right here. Don't let that confuse you. So we're going to have the integral from a to b of 3 with respect to x. And we know that the antiderivative of 3 is 3x. So what we would do, we would take this and plug it in. So our antiderivative is 3x. Again, we have our limits of integration, b and a. So we plug those in. And if we look back above to our properties here, you can see that this first property that we had, if we plug in 3 for c, we get exactly what we ended up with. So that's a good verification check. We can consider another example. So now we're going to consider integrating y being equal to x over some interval, again a to b. And we're just going to first look at what this function looks like on a graph. And we know that y is equal to x, so when x is equal to b, y is equal to b. And if we looked at the area under the curve here, that's just simply going to be equal to b times b divided by 2. So that's what we would expect when we integrate this. But we don't know how to integrate this yet, because we need to know the antiderivative of x, or essentially some capital F function that when we take the derivative of it, it gives us x. And unfortunately, this point is where we're going to look at trial and error. So we're going to consider a few functions to try to find this antiderivative. So we know if we take the derivative of sine of x, we get cosine of x. Comparing that to what we need, that's not even close to x. If we now take the derivative of x, well, that's going to equal 1. If we take the derivative of a constant, well, again, no dice. And if any of these are confusing, go back to the previous videos where we went through all of these. Now we can even throw in some functions that we haven't looked at before. So let's look at the function e raised to the x. And we don't know how to do this derivative, so let's do this derivative. And there's a lot that's going on here, so we're just going to scroll down and I'll walk through it all. So we take that function e to the x, use our definition of the derivative right here. With algebraic manipulation, we pull out this e to the x. We simply have this limit right here. And this is a headache of a limit because if we take h going to 0, we essentially get a 0 over 0 condition. And we know that that is not fun. So we're going to do a substitution. Let's say that y is equal to e to the h minus 1. So as h goes to 0, y is also going to go to 0 because this term goes to 1 and 1 minus 1 is equal to 0. And we can also say that h is equal to the natural log of y plus 1. So our limit that we were not looking at gets substituted into this limit, and we can throw this y into the denominator simply by having a y raised to the minus 1. Typo there, it looks like. So we know that we can represent this term like this here. And now we need to look into another new thing, which is going to be the limit of composite functions, because now we're pretty familiar with limits. So let's say we have a function g of x, and we're going to take that limit as x goes to a, and let's say it's equal to b. Now we're going to have another function, f of x, and it's going to be continuous at b. And if both of these are correct and true, we can actually say that the limit as x goes to a of f of g of x, we can throw that limit actually inside of the parentheses right here. And we arrive at this term right here to evaluate. So if we do that for what we got up here, down here, we plug that limit in to the parentheses for the natural log. And it turns out that this right here is actually going to be equal to the constant e. And e is going to represent Euler's number, which is approximately equal to 2.71828, I believe. So now that limit is equal to 1 divided by 1, or simply a 1. So now our sad face limit here is no longer sad because we know that's equal to 1, and we just have e to the x times 1. And what this says is that our derivative of e to the x is equal to e to the x. That seems a little bit weird given what we've been looking at for the rest of these functions, but this is correct. This is the derivative of e to the x. But all work aside now, we know that this is not equal to x, so a whole lot of work, all for nothing. So I guess we keep trying. And we can try another weird function, so we're going to say that we're going to look at the derivative of ln of x, or the natural log of x, because we dealt with a little bit of that up here. And again, we have more tricks in the bag because we're a mathematical magician. So we're going to say that y is equal to the ln, or natural log of x. And what we're going to do is we're going to raise everything. So we're going to have e to the y being equal to e to the natural log of x. And now we're going to take the derivative of this. So if we take the derivative of the left side, we would say that dx of e to the y. And we know here we need to use that chain rule that we learned before. And we know what the derivative of e to the y is with respect to y because we just did it in terms of x. And then we simply have dy dx. And if we look at the right-hand side, we know that e to the ln of x is simply going to be equal to x, and that the derivative with respect to x of x is going to be equal to 1. We have our left-hand side and our right-hand side. But notice here that e raised to the y, which was given here, which is equal to e to the ln of x, which is here, which is equal to x. So we could also say that our left-hand side is equal to x dy dx. So let me box off a little spot for me to work in. So if we say our left-hand side is equal to our right-hand side, we say x dy dx is equal to 1. Or we could say that the derivative of y with respect to x is equal to 1 over x, where this y that we're looking at is equal to this, which is equal to ln of x, which is what we're looking for right here. We would say that the derivative of the natural log of x is equal to 1 divided by x. But again, this does not equal x. So we keep moving forward. And we're starting to run out of functions, but we can look at another function, just our power function. So we know that the derivative of this is going to be n times x to the n minus 1, where n can be anything. So we ask, is that equal to x? And now we're starting to get somewhere. Because if we say that n is equal to 2, we're off by a factor of 2. But we know that if we have the derivative of a constant times some function, that's going to be equal to the constant times the derivative of that function. And if we check this out, if we say the derivative of 1/2 x squared, and that is equal to x. So if we go all the way back above, we can say that this integral that we were originally investigating is equal to 1/2 x squared evaluated at b and a. And scrolling up just to fit everything in screen, we know here on our interval that we were looking at, we could say that a is equal to 0 because we are starting right here at origin and comparing that to what we calculated for the area. We have a matching term, so we know that our integration worked. And hopefully from all of this, you can see why integration isn't as easy as differentiation. We did learn something along the way about differentiation and limits. So now we're starting to encompass all of the things that we've learned in this calculus course so far to move forward. So you can see the difficulty and complexity of things is starting to escalate, and in the next video, we'll look even more at integration, Again, if you learned anything new, found anything useful, I hope you did. Please like, comment, share, subscribe, and we'll see you in the next video. Thank you for watching.